Alrighty, howdy folks. I'm going to continue with 2.2. Let's call this as part 2. Boy, when I was trying to record that, I just felt very tired. Maybe I'll have a bit more energy today. Alright, what should we do? I should click on this guy and start the slideshow. Okay, let's go to problem 26, which is this. Recall that we are talking about separation of variables technique to solve first order differential equations, right? And the idea was that we should be able to separate the x's and y's. Can we do this? I say yes. It looks like this one has a sine 3x and a dx, which are all x terms. But this one has a 2y dy, which are y terms, but it also has a cosine cube 3x. So maybe as a first step, let's do that. And now can we separate? Right? Oh, yeah, we could divide both sides by cosine cube of 3x, and that should do the trick. So the right side integral is fairly straightforward, and the only problem is the left one. Well, could I use a substitution rule? Especially use substitution. How does that work? You should, inside this integral, please pay attention. Inside this integral, you want to set u to be something so that du is also inside the integral. Okay, set u to be something inside the integral such that du is also inside the integral. For example, if you say if you say u equals cosine 3x, then du is going to be negative 3 sine 3x dx, right? That negative 3 times, that negative 3, which is a constant multiple, you can ignore that. But do we have a sine 3x dx in du? Yep. So that's why that is a good substitution, right? And since we need just sine 3x dx, let's go ahead and solve for that. That means I'm saying divide both sides of this du by a negative 3. So that sine 3x dx is negative 1/3 du. Now we are ready to make our substitutions. So this, for sine 3x dx, we'll plug in negative 1/3 du and 1 over u cube, right? And then it's a straightforward integral. U to the negative 3 du integral is u to the negative 3 plus 1 over negative 3 plus 1. And come back and plug back what u was. U was cosine 3x, so this becomes cosine square 3x. Cool? That's the idea. Now, I like this one. Whoa. Can we separate x's and y's in this one? Now check this out. Could we factor out on the top from the first two terms? Rather, maybe I should use that phrase. Let's factor this by grouping. xy plus 2y, form that into one group, and minus x minus 2, form that into a second group. And so you have y times x plus 2, factor out a negative 1 times x plus 2. Okay, that's what I did. Similarly, factor out a y from the first two terms in the denominator, y times x minus 3 plus 1 times x minus 3. Lo and behold, on the top, you see this x plus 2 as being a common factor once again. So that means we can factor out an x plus 2, giving us x plus 2 times y minus 1. In the bottom, we'll have x minus 3 times y plus 1. Cool. Now we can separate the things and say y plus 1 over y minus 1 times dy. Now the question is, how do you integrate that? Well, I showed you earlier. We could be a bit clever about this one. We could do long division, or we could do something clever. That is, express the top in terms of the bottom. That means on the top, make sure you have a y minus 1. So write this y plus 1 as y minus 1 first. But then you have to do something, right? You have to, if you add 2 to y minus 1, you'll get back your y plus 1. You see that strategy? I'm saying y plus 1, write that as whatever the denominator is, which is y minus 1. But then now ask, hey, what should I do to make y minus 1 into y plus 1? Well, you add a plus 2 and you get y plus 1, right? Now, tell me how you proceed with the right-hand side stuff in a similar fashion. You should write x plus 2 as what? Whatever the denominator is, x minus 3. You cannot obviously leave it like that. You must do something so that that x minus 3 actually becomes x plus 2. You can accomplish that by adding a 5. Right? Exactly. And so, I did that in the next step. This is the idea. Then we can separate the fractions, separate them into two fractions, y minus 1 over y minus 1, which is 1, plus 2 over y minus 1. Integrate. You're done. Cool. Next. Separation itself is not so difficult. Oh, by the way, pay attention to this. Could I divide both sides by dy? You see what I'm saying? Could I divide both sides by dy? Wouldn't I be separating the x's and y's if I do that? X plus square root of x over dx, all are x terms, and y plus square root of y over dy, on the right hand side, all y terms. Ta-da! No ta-da. Why, what's wrong, man? Well, what's wrong is you cannot have a dx in the denominator. Okay? You must have dx on the numerator. So that means we must multiply by dx, both sides, and we must divide by x plus square root of x. Okay? And my dog is sleeping right next to me and she's snoring. I hope it doesn't bother you guys. I don't know if you can hear it either. So if the microphone catches it, that's my dog snoring and not anybody else. Okay, sorry about that. So we get this. Now the only question is, how do we integrate this? This integral is pretty interesting one. Any thoughts? Anybody? Think about it. Okay. If you want to pause the video, please do that and see if you can challenge yourself to solving this one. But anyway, so let me pick one of them, because once we know the solution to one of those integrals, the other one is exactly the same, except in place of x we have a y. Right? U equals square root of x and u square equals x. I like solving it this way. U equals square root of x, u square equals x. And so 2u du will become dx. Alright? And so we are ready now. So for dx, we'll plug in 2u du. For x, we'll plug in u square. And for square root of x, we'll plug in u. and that means we can factor out a u from the bottom, and so u's cancel, and this reduces to 2 over u plus 1, and which is 2 times natural log of absolute value of u plus 1 plus c. Plug back u equals square root of x, and we're done. Cool. Almost done. So the original integral now becomes 2 natural log of let me pause here and get the dog out of my room. Okay, I'm back. Sorry about that, guys. Let's see. Where was I? We got to all of this, and here I guess I need to point something out. Maybe some of you had this question. Hey, how come you put that plus c on only one side, man? We had the integral on left hand side and the right hand side. What happened to the one on the left hand side? Shouldn't you say plus c there? Well, don't say plus c on both sides, because that way the constants will cancel. On the other hand, if you wanted to say, well, okay, I won't do that, but I promise you some blah blah plus c1 on the left hand side equals some blah blah plus c2 on the other side. Nothing wrong with that. Okay, the 2 natural log of absolute value of blah blah plus c1, and on right hand side 2 natural log blah blah plus c2, perfectly fine. But then notice, couldn't you subtract the c1 from both sides, so you will have blah blah plus c2 minus c1? Now, isn't c2 minus c1 just an arbitrary constant that you could replace with a single c? That's the idea. So when you have something like this, when you have an equation like this, you do not have to put the constant on both sides. One side suffices. Okay? All right. Next. Or, ooh, what'd you do there, man? I think I shouldn't say that C is not the same as this C. Yep, I changed the font. Again, you know, what's that? I divided both sides by 2, and so we have natural log of this plus is equal natural log of this is equal to natural log of that plus C over 2. Okay, that's what I have, C over 2. And then I said e raised to natural log of that would be just this quantity. And of course, the assumption is that we have picked, well, no. The assumption is y is greater than 0 and x is greater than 0. That must be true because we have square roots. So obviously, square roots indicate that you must have x to be greater than or equal to 0. So all that is built into it. So this is okay. All right. That's the idea. Oh, okay. Now I have an initial value problem. Good. So how do we solve this one? Separation of variables. Let's first solve the differential equation. Then we will apply that initial condition of y of 2 equals 2. Okay, how do we integrate dy over y square minus 1, which is the same way as integrating dx over x square minus 1? The denominator can be split into, factored into x plus 1 times x minus 1. And now, if we do a partial fraction decomposition, we get 1/2 of 1 over x minus 1 minus 1/2 of 1 over x plus 1. Okay, I really recommend you to watch the videos that I posted about integration, and there is a section rather on partial fraction decomposition. I cover all kinds of techniques there. All of those things will come in very, very, very handy. Okay. So we know we have shown you clearly how to separate these into partial fractions. It's a quick and easy way of doing that. And so this is 1/2 natural log of absolute value of x minus 1 minus 1/2 natural log of absolute value of x plus 1. With what happened to the minus, man? Aren't you supposed to have a natural log of absolute x minus 1 minus natural log of absolute value of x plus 1? Yeah, but there's a property of logarithms. Natural log of a minus natural log of b is natural log of a over b. Right? Natural log of a over b is natural log of a minus natural log of b. I invoke that principle, and here is the answer. Okay. Thus the solution is this, and of course we can multiply both sides. Ooh, I did not do that. I didn't simplify it. From the initial condition y of 2 equals 2. Ooh, look at this. I like this. This is what I think I alluded to in the previous video. Should we take, looking at this y minus 1, that y is greater than 1? Or should we take this as y is less than 1 so that we can remove the absolute value sign around it? So which interval should we consider for x and for y? But then the condition tells us exactly what to do. The condition says when x equals 2, y will equal 2. So you must pick an interval such that x equals 2 is in that interval and y equals 2 is also in that interval. So that tells us that we must pick x to be greater than 1 and y to be greater than 1. And so that means if x is greater than 1, then clearly x minus 1 is greater than 0, and we can drop the absolute value. X plus 1 will automatically be greater than 0. So that means x minus 1 over x plus 1 is guaranteed to be positive whenever x is greater than 1. Would you agree with that? Let me repeat that. Would you agree that x minus 1 over x plus 1 is guaranteed to be positive when x is greater than 1? Similarly, would y minus 1 over y plus 1 be greater than 0, will be positive when y is greater than 1? Okay, on with that piece of information. We can remove the absolute value signs around those and then write like this. And now we'll apply the condition. Excuse me. I see. Well, I multiplied both sides by 2 and then raised to a power of e, and also replaced e to the 2c with a c. Maybe I should have made it into a slightly different c, but hell won't break loose. Okay, so we do that, and now I think we need to apply the condition. Y of 2 equals 2, that is, plug x equals 2 and y equals 2 into this one. And when we do that and solve for c, we get c equals 1. So that means the solution is y minus 1 over y plus 1 equals x minus 1 over x plus 1. Cool. That's it. So this is part 2 of section 2.2, and you are responsible for 1 through 48, folks. All right. Thank you.